In this session, we are going to see about asymptotic notations. So, what are these asymptotic notations? These are some mathematical notations which are used to represent the efficiency of an algorithm. So, in the previous sessions, we have seen how to find the time complexity and how to find the space complexity. So, those two terms define the efficiency of an algorithm. So we need some meaningful notations to represent those efficiency of an algorithm. And for that, we are using asymptotic notations. So there are basically 5 types of asymptotic notation, but to compare orders of growth, computer scientist uses major 3 notations. The 3 major notations are big O, big omega, and big theta. So let us relate two non-negative functions t of n and g of n. So what is this t of n and g of n? T of n represents an algorithm's running time and g of n represents simple function to compare with the count that we have in t of n. So this might look like Greek and Latin to you, but you will understand it in further upcoming slides. So let t of n be order of distance covered by a vehicle, and the g of n, this is the algorithm for which we are going to compute the efficiency, and this algorithm is the one which is defined. So this g of n can be a jet. See this t of n is the function for which we are going to determine, and g of n is the one which we are going to compare with. So this g of n can be a jet. So jet covers maximum distance. So the distance covered by a vehicle, this is maximum distance. So for representing maximum distance, we will use a notation called big O, and that is worst case. So maximal amount of distance covered. In terms of algorithm, it is the maximum time taken, and technically we will call it as upper bound. Else this g of n can be minimal also, the distance covered by small distance covered by a vehicle. So which vehicle we use? We use a bicycle. So that term we call it as omega. So which will be the best case? The technical term is lower bound. So best case means least time taken. Here least distance covered. We need a term to imply something which is in between these two. So smaller distance is covered by a bicycle, larger distance is covered by a jet, somewhere in between, average distance. So assume that we are using a car. So that is represented by theta. So this is average case, which is in between your best and your worst. And in technical terms, we call it as tight bound. So I believe you all understood what is t of n and g of n. So t of n is the function for which we need to find the efficiency, or the algorithm for which we need to find the efficiency. And g of n is the function with which we are going to compare. So with this we can compare, or with this we can compare, with this we can compare. So coming to big O notation, you have a formal definition. A function t of n is said to be in order of g of n, which is denoted by t of n belong to order of or big O of g of n, if and only if there exists some positive constant c and a non-negative integer n naught, such that this condition should be satisfied. That is, t of n should be always less than or equal to some constant into g of n for all n greater than or equal to n naught. Somehow you need to by heart this. For big O, this is the condition to be satisfied. So we have a graph for that. So what does the x-axis mean? It is the input size, and the y-axis is your rate of growth. So your input might start from 1 and it may go till million number, but there will be one particular point for which this condition is satisfied, that is t of n will be less than or equal to c into g of n. So that is the point represented as n naught, and before that you might have some values. For that values, this condition might not be satisfied. So that is why here I am representing as it doesn't matter. So for all these cases it doesn't matter. So from this point only, from this n naught only, this condition holds. This is for big O. Similarly, for big omega, you have a function t of n and g of n, and you are going to compare these two, and the notation used will be big O, and this should satisfy a condition t of n should be greater than or equal to c of g of n, c into g of n. So for big O, it was t of n is less than or equal to. For big omega, it is t of n greater than or equal to. So similar type of graph we have. So we are least bothered about the part which is represented in doesn't matter, and always this t of n will be greater than c into g of n. That is why t of n comes above c into g of n. And next comes the formula for big theta, and similar type of definition. The condition here is t of n should be between two functions, g of n and g of n. Here c1 constant into g of n, here c2 constant into g of n. So we have two constants c1 and c2 in big theta notation, and the graph is given like this. So t of n will be somewhere in between the first c1 into g of n and the second one c2 into g of n. So you just by heart these formulas for big O, big theta and big omega. Here comes the order of growth. So we will be representing the efficiency of an algorithm in terms of asymptotic notation. So before we solve some problems in asymptotic notation, you should know in what way the performance of an algorithm is represented. First, it can be order of 1. So that is constant representation. Next one, order of n, which is logarithmic. Then n, which is linear. Then n log n. Then n square, that is quadratic. N cube, cubic. 2 power n, which is exponential. And n factorial, which is factorial. So this is how the order of growth increases. So next comes the properties that are there in asymptotic notation. So here comes the general property. So if there are two functions f of n and g of n, if f of n is order of g of n, then any constant a into f of n is also order of g of n. So here is an example for that. You have a function f of n represented as 2n square plus 5, and g of n is n square. So if you apply values for a in this function, 7 into f of n is equal to 7 into the function, so which is given as this, which also satisfies order of n square. So we all know what formula should be met for satisfying this big O. So this is what is general property. So similarly, the same general property will hold for both big theta and big omega as well. Next comes the transitive property. As per the transitive property, if f of n is big O of g of n and g of n is big O of h of n, then f of n is equal to big O of h of n. So here is an example where f of n is n, g of n is n square, and h of n is n cube. So n is order of n square and n square is order of n cube, then n is big O of n cube. This property, transitive property, will be satisfied by both big theta and big omega as well. Next is reflexive property. The reflexive properties are always easy to understand after this transitive. That is why we have placed it in the third one. If f of n is given, then f of n is big O of f of n. So any function f of n, it belongs to big O of itself. So that is what is reflexive. So if x is equal to f of n, y is equal to big O of f of n. These tie themselves in reflexive relation always. Here is an example. If f of n is n square, it is order of n square. So this property is also holded by big theta and big omega. Next is symmetric property. If f of n is big theta of g of n, then g of n is big theta of f of n. So this is symmetric property. Here is an example. If n is equal to n square and g of n is equal to n square, then you can write f of n is equal to big theta of n square and g of n is equal to big theta of n square. So this property holds only for this big theta representation. It doesn't work for big O or big omega. And the last property is transpose symmetric property. As per this property, if f of n is big O of g of n, then g of n is big omega of f of n. So here is an example, and this property holds for both big theta as well as big omega, and not for, this property holds for big O and big omega but not for big theta. So we will solve some problems based on asymptotic notation. The problem here is we need to prove that 3n plus 2 belong to big O of n. So here Tn is 3n plus 2 and g of n is n. So to prove that this 3n plus 2 belongs to big O of n, we all know what condition has to be met. T of n should be less than or equal to some constant into g of n for n greater than or equal to n naught. We apply T of n, the value of T of n, the value is 3n plus 2. So 3n plus 2 should be less than or equal to some constant into g of n. G of n is n. So now we need to find the constant value and n naught, which is a non-negative integer. So we will do it by trial and error method. So first we will start taking c as 1, then n as 1, 2, 3, 4. It doesn't hold. Next we will start assuming c as 2 and then n as 1, 2, 3, 4. That also doesn't hold. Then we will start taking c as 3 and n as 1, 2, 3. It also doesn't hold. So we need to apply the value for n. Substitute n is equal to 1 and c equal to 1 in this equation. So if I apply the values, I have to check whether this condition is met or not. So when n is 1 and c is 1, 3 into 1 plus 2 less than or equal to 1 into 1. So 5 is less than or equal to 1? No. So likewise, I have to try for different values of c and different values of n. Then I am taking c as 4 and again n from 1 to 3, 4. When n is 1, 3 into 1 plus 2 less than or equal to, c value is 4. 4 into 1. 5 less than or equal to 4? No. But when n is 2, when I substitute value n as 2 and c as 4, this condition is satisfied. So it becomes true. And when n is 3 also it is true, and when n is 4 also it is true. So what we can conclude, when the value of c is 4 and n is 2, this condition is met. That is 3n plus 2 is less than or equal to 4 into n. So since this is true, 3n plus 2 belongs to order of n. So this is how we need to explore different values of C and different values of N and check whether the condition is met to prove that the particular function belongs to a particular asymptotic notation. It might be either big O or big theta or big omega. The corresponding condition should be checked. We will solve one more problem. So here the problem is show that n into n minus 1 by 2 belong to big O of n square. So what is t of n here? I am expanding this n into n minus 1 by 2. So it is n square by 2 minus n square by 2. And g of n is n square. So we know that the condition to be satisfied for big O is t of n should be less than or equal to c into g of n. So we substitute t of n square by 2 minus n by 2 in the place of t of n and n square in the place of g of n. Now we have to take different values of c and n. Since the given function t of n is in terms of n square by 2, let me start assuming the values from 1 by 2 for c, and for n we will start with 1, 2, 3. So when c is 1 by 2 and n is 1, the condition holds. By applying n as 1, by substituting n as 1 and c as 1 by 2, the condition holds. When c is 1 by 2 and n is 2, at that time also the condition holds true. When n is 3, that time also the condition holds true. So we assign c is equal to 1 by 2 and the condition starts true from n is equal to 1 onwards. So that is why I am placing n naught as 1. So from this we can say that the given function n into n minus 1 by 2 belong to big O of n square. So, since the condition is satisfied. So another problem, we need to find the upper bound of running time of a cubic function. So upper bound means big O, worst case. So the given function f of n is 2n cube plus 4n plus 5. So we all know what condition is to be satisfied. So f of n should be less than or equal to some constant into g of n. This is the condition that is to be met for big O. This is the condition. So the given function is 2n cube plus 4n plus 5, which should be less than or equal to some constant into g of n. So what can be the value of g of n? We need to find it. So in the previous problems, we were given both f of n and g of n, and we applied different values of c and n to check whether the condition holds and proved. This time we are given f of n and we are asked to find the upper bound. So we need to find the value of g of n. So what am I doing? I am placing all the equation representation in f of n, that is 2n cube plus 4n plus 5, which should be less than or equal to, I am not having any values, I am not taking any values of c, we will keep it c as such. And for g of n, what am I doing? Here, since it is 2n cube plus 4n plus 5, I am writing the same numbers here as well, but all in the highest powers, in terms of highest powers. So highest power is n cube here. So the same representations, 2n, 4n, 5 here, but I am including the highest power in all these notations in the right hand side. So it becomes 2n cube plus 4n cube plus 5n cube. So when I add all these, it is 11n cube. Yes. So what can I infer from this? C can be 11 and g of n can be n cube. If that is the case, definitely 2n cube plus 4n plus 5 will be always less than or equal to the constant 11 into g of n, which is n cube. So this is what we have found. So similarly, we can use an alternative method also to find such upper bound, which is a tabular approach. So how will this tabular approach work? So you will have this f of n and g of n. You can take any value of as g of n, like n cube. Since here f of n is in terms of n cube, we will definitely, your g of n should have terms in n cube only. So the value of c alone, we have to fix it. So here we did it in generalized way by adding all 2n cube plus 4n cube plus 5n cube. But here we are going to try uh, with 3n cube. You can start with 3n cube. So apply different values of n in f of n and g of n, and we can find when n is 3, this condition holds. That is, f of n is less than or equal to c into g of n. So this is another solution. So as per this method, the solution is c is 11, g of n is n cube. As per this tabular method, the solution is c is 3 and n naught is 3. And g of n is same n cube. So you can use any of the approaches, either generic method or tabular method, but somehow we have to find what will be the upper bound, that is g of n, and the corresponding constant. The next problem is to find the lower bound. If you are given a function f of n, how to find the lower bound? So we all know this condition should be met. The function f of n should be greater than g of n, some constant into g of n. So the given function is 3n square plus 2n plus 4. This should be greater than some constant into g of n. So what can be there in g of n and what can be there in constant c? So since here it is 3n square plus 2n plus 4, obviously I can take the value of g of n as 3n square. So this 3n square plus 2n plus 4 should be definitely greater than this 3n square. So whatever terminologies are there in f of n, the same terminologies can be considered in g of n as well. So but here I am not including this 2n plus 4, only 3n square. Why? Only then this f of n will be greater than this g of n. So g of n is n square and constant is 3. Similarly, for constant 1 also the same condition holds. That is 3n square plus 2n plus 4 is greater than or equal to 1 into n square. That also holds, because obviously this will be greater than n square. When c is 1, it is n square. So it holds. So like this I can prove for what value of c this f of n can be greater than or equal to g of n. This is for lower bound. Similarly, we can find the tight bound. Tight bound means my f of n should be between two things. So the condition to be satisfied is f of n should lie between c2 into g of n and c1 into g of n. So between these two my f of n should lie. So you are given with f of n, which is 6 into 2 power n plus n square. In the order of growth, we have seen that 2 power n is greater when compared to n square. Okay, 2 power n is greater when compared to n square. This is quadratic and this is exponential. So always exponential is of greater complexity than this quadratic. So you remember that point. So I am writing my f of n here, and this is g of n into c2 and this is g of n into c1. So I need to find now two constants, c1 and c2, and my g of n. So what can I place? So this is my f of n. So it is having one n square term also. Removing the n square term, I am taking this term alone and I am putting in the left hand side. So obviously 6 into 2 power n will be less than or equal to 6 into 2 power n plus n square. Fine. Then here I have to write the maximum. So f of n is 6 into 2 power n. Why can't we try with 7 into 2 power n for the right hand side to be greater than f of n? So like this I have to select the function g of n. So for this one it should be lesser than the f of n, and for this one it should be greater than f of n. So f of n is equal to big theta of g of n, where g of n is nothing but my 2 power n. So here also I am having 2 power n, here also I am having 2 power n. The constant here is 6 and the constant here is 7. So it lies in this condition. So hope You understood what asymptotic notations are, the conditions for big O, big theta and big omega, the order of growth, and how to solve a problem to prove whether a given function belongs to big O or big theta or big omega, and to how to find the tight bound, lower bound and upper bound of any quadratic function or any function.